In this video, I want to discuss the idea of page replacement. So now we're going to basically look at the case for, I want to read something, right? I want to load something to memory because I need to use it for an operation, but I don't have any space. So somehow, right, I basically need to make space for it. I need to pick some sort of a victim and replace it with something else. So let's take a look at this process. So obviously, right, if a page fault occurs and I have no empty space, right, I need to make space for the new page that I'm going to load up. So I have basically these 4 different steps that will occur. So imagine, right, we have a page fault. What do? The first thing, right, is we basically need to pick a victim page, right? So we need to pick a victim, right? That's kind of step 0 almost in this picture here. So we pick the victim, and we're going to talk through algorithms in a minute that do this. Once I pick them out, I need to swap them out, right? So I have step 1 here where I say, you know what, the victim, I still need them, right? That's still a program that's running somewhere. It just hasn't used the page, in a while, for example. I need to basically save it to the hard drive. Once it's saved to the hard drive, then I need to basically update my page table. So my page table, right, I need to set the bit for that particular page to something that's invalid, right? So I need to basically mark that as no longer available. Okay, so that's kind of my second step there. My third step, right, is basically to bring in my new page, right? So I have something in the backing store, right, my hard drive, somewhere. Bring that in to the place I just made available. And then once it's there, right, I have my step 4, which is go to the page table and set that valid bit, right? So now that thing is available. So I have these 4 steps, right? I move something out, update the page table, move something in, update the page table. So I'm going to need to follow that same process. Again, the main work, right, or the thing kind of that affects the most stuff is going to be the selection of the victim frame. As one quick note here about optimization, oftentimes what people do is they add something called modify bit. So they actually have kind of a third column here, called M, and they'll basically have a bit there that represents, has this page been modified since it was loaded from the secondary store? Because you can imagine, right, is that I can basically afford to keep everything here, right? I don't need to worry about kind of making space in my secondary storage because it's got, all this space there. So if I have basically my bits here to represent, modified, well, if I have a page, for example, that I'm going to move out and its modified bit is 0, what that basically implies is nobody's changed this page since I moved it into the main memory. So I can just delete it, right? It's still going to be there in the secondary storage, right? I'll be able to get it back when I want to. So that kind of saves me, a write operation. And so yeah, that's the kind of a very typical thing that's done, right? Is just to have this extra bit here. Are you a modifier or not? Because if you're not, I don't need to worry about writing you. Obviously, I'm always going to need to be worried about bringing people in, but at least when writing them out, I can maybe kind of skip it for some of the frames that haven't been changed. Okay, so having gone through that stuff, let's talk about the idea of a page replacement algorithm. A page replacement algorithm is basically just something that picks the victim frame, right? It knows, that I need to, add some new page because there was a new, some sort of page fault occurs, and it knows, what's available, and it's going to pick from that, what should it cycle out. So those are called page replacement algorithms. Now, all the algorithms we're looking at are basically going to be parameterized on some sort of a size, because I can have a page replacement algorithm that stores, 10 pages or 20 pages or 30 pages. They'll all kind of, basically be able to, size according to how you want. Because obviously, the more memory you have available, the more pages your algorithm has to work with. So they're all going to vary a little bit. Now, for each of these algorithms, what we're going to look at, or what we're going to use to judge their effectiveness, is this idea of a reference string. So a reference string is going to be some sort of set of sample reads that happens, right? So it's like I need to access this page, this page, this page, this page. How does the algorithm fare? We'll call that a reference string. And our primary metric here is basically going to be the number of page faults. So obviously, lower page faults are better, right? More page faults means more, basically you're going to slow down your system because it takes you more time to go to the main memory, figure out where things are stored, right, and then load them up. So less page faults is better. So for reference strings, right, we'll kind of basically stick with one, right, and use it for all the different algorithms. That's kind of the best way, right? Let's just basically compare things. So let's say, right, we looked at a program that was running. If we were to access memory, it would probably look something like this. You can kind of look at this kind of string over here. So access, this memory, memory 100, memory 432, memory, 101, so on and so forth, right? I can have all these different things being accessed. And this is, this is fine, right? This is how a table program works. For us, we'll actually simplify this down, right? So our reference string wants to sort of encode this information of these are the pages that are accessed, but we make things a little bit simpler. Main things we make simpler is we basically, truncate these things a little bit. So we just call this, page 1, page 4, page 1, page 6, page 1, page 1. We're not going to kind of look into each individual address because obviously pages are more than one address. So if I have things that are kind of all together in the same page, I kind of want to group them together. So I'm going to basically just look at those most significant digits, right, and call that my actual page number because my page contains many different things. And so I'll simplify that down, and that's where you see the single digits over here, right? So that's just kind of the leading part of the address. The second kind of change here, right, in this simplified string that we'll end up using for our analysis is we kind of combine things that are adjacent. So over here, you may notice that I have basically, this is 01, 02, and then 01, 03, right? Those are kind of next to one another. And before I said I'm going to simplify by dropping the front part of it. Well, if I do that, right, I basically get 0101, those two, right, if I'm accessing the same page right after another, well, basically I don't even need to worry about that, right? It doesn't really make sense for me to analyze that sometimes because, because it's like I know the page is going to be available. So we'll skip that in a few examples. We'll show it a couple other ones just so you guys get the idea, but in general you can kind of skip that and not have to have the duplicates in your reference string. All right, so that's kind of what we got. We're going to now basically spend some time to look at our different page replacement algorithms and figure out how well they perform, right? Meaning how many page faults do they trigger given some specific reference string.